Welcome to another lecture on digital electronics. In this video, we'll be seeing what is a race around condition in the JK flip-flop. Before that, let us draw a JK flip-flop using NAND only gates. So like we have done in SR, here also we are doing JK flip-flop using only NAND gates. So what is the construction? Same, you have NAND gates to provide our inputs, which is J and K. There is a clock which is connected between both of these signals. And if you remember, J had one more input coming from Q bar, right? So this is how the connection we did. Same thing we are doing, just the fact that we are connecting it internally, not from outside but from internally. So this is still Q bar which is coming in J, and the crisscross connection which you already had previously, right? Similarly, here also you have K as input, clock is connected between these two, and K was multiplied by Q. So this is still your Q connection which is coming, and this Q also went as a crisscross connection to this NAND gate, right? This is your preset signal. This is a clear bubble, indicates these are active low signals. This is your output Q, and this is the complementary output Q bar. So this is your basic flip-flop, JK flip-flop using NAND gates only. Just to clarify the connections, we have drawn this circuit. Now let's move to the race around condition in the JK flip-flop. So before we go to race around condition, there is some concept called as propagation delay. What is this propagation delay? It is nothing but the time delta t taken for this entire flip-flop to move its input, as in when I apply the input and the time I get the output, the time duration between input to output, that is called as the propagation delay, and which is mentioned here, that is delta t. So now what is race around condition and why it occurs? There are three conditions because of which race around condition occurs, especially in JK flip-flop we are talking about. So what is this race around condition? The very first thing in the race around condition is if we are using level triggering of the clock. Second condition, J equal to K equal to 1. So if you remember JK flip-flop and the truth table, 0 0 0 1 1 0 1 1. For 0 0 it was Qn. For 0 1 it is 0, 1 0 is 1, and for this is Qn bar. So for J equal to K equal to 1, my Qn plus 1 is complement of Qn, right? So this is second condition because of which it occurs. The third condition being delta t is very less than your time of the clock, right? Delta t is very less than the time of your clock. See what happens. I will draw the graph and make you understand how this works. Time period, we will denote this as of the clock signal. So what is the clock signal? This is your clock signal, right? Since we are using level triggering, say I use positive level trigger. What does this mean? This is negative level, this is positive level. This is positive edge, this is negative edge. This means that when this part of the clock comes at the input, that is the time when the flip-flop becomes active and it starts showing its corresponding output with respect to the input. What is the input that we are giving? J equal to K equal to 1. For J equal to K equal to 1, what is my output? It is Qn bar. It is complement. Okay. So let us assume that at any one condition, the output Q is equal to 0. So my clock pulse, this arrived level, positive level. Now the output will come. What is TP? This is your TP. And what is delta T? Time taken to show the output from input to output, right? So initially say the output is Q bar. Qn is equal to 0. If it is 0 for j equal to k equal to 1, what is my qn bar? It is the complement. So it will become 1. So it is 1. So my new output became 1. My input is going to remain same, j equal to k equal to 1. What does my output change to? It changed to 1. So since it is level trigger, again for j equal to k equal to 1, I will have the new output as qn bar. What is qn bar now? 1's complement, which is 0. So this signal will turn down to 0. Now my new output is 0. When my new output is 0, j is equal to k is equal to still 1. What is qn bar? It is qn's complement, right? So it will become 1. So this will go high. And this will continue till you have a positive edge. So at this point, I am not certain of the output. I am not sure whether I will have a 1 here or a 0 here because of this toggling, and this is called as race around condition. So to remove this race around condition, what we should do? We should make sure first we should not use a level triggering because it has an entire duration for which the output keeps on toggling. So we should either use a positive edge, triggering, or use a negative edge triggering, which is this. So at that instant the output will come from the flip-flop. So that is the first thing. Second thing is a time duration of the signal. So if TP, here my delta t propagation delay was very less than the clock signal. So what I have to do? I have to make this propagation delay delta t much larger than my clock signal. So in this case, I will be able to remove the race around condition. So if this is your delta t propagation delay, very small propagation delay, this is your delta t. If this becomes larger, if this delta t becomes larger than this TP, so in a single clock pulse only once your output will change, not multiple times. So these are the methods through which you remove the race around condition. Another method to remove the race around condition is to use master and slave JK flip-flop. So level triggering, by not using level triggering and edge triggering, of course you can remove the race around condition. Second condition is by increasing the propagation delay or making your clock signal time very less compared to the propagation delay. But this is a bit tedious to do. The last one is with level triggering. If you are using master and slave JK flip-flop, you can remove the race around condition. So in the next lecture, we will be discussing how master and slave JK flip-flop works. I hope the concept of race around is clear. I will stop the video here.